Okay, here's an example of problem one. I think this is the pink version. So I gave you a bunch of x values. I gave you a bunch of f prime values. The f prime values are going to tell you the slopes of the tangent line for the f function. So in other words, these values tell you if your f function is increasing or decreasing at those points. Another very important thing is that all of the critical values are represented here. So between -5 and -3, we couldn't have a function that turned around at all. Because if it turned around, I know that f prime would be 0, which would make it a critical value, which would make there be a critical value where it turned around, for example, at -4. But since there isn't a value that I gave you at -4, you know that it can't have turned around there. So in other words, if it is decreasing at -5 here, I also know it's going to be decreasing at -4.5 and negative 4.0001, and it doesn't flatten out until it gets to -3. So that was really key here. I imagined that this was going to be very fast. Here's what I imagined you were going to do. All right, so we're decreasing steeply. We have flattened out. Here we're decreasing again. Derivative does not exist, so there's a cusp or a corner here. So maybe some kind of thing like that. Here we are increasing. Here we are increasing steeper. Here we are increasing, but not that steep. Here we are flat again. And here we're decreasing. All right, let's look at answers. So on what interval is f increasing? So f is increasing starting right after 1, and we're increasing through here, and we're increasing through here, and we're increasing, and we stop increasing right here at 9. So from 1 to 9 is the interval where we're increasing all the way through there. Where are we decreasing? So -5 is decreasing. Some people assume the domain was from -5 to 11, which is fine. Other people assumed all real numbers, also fine. But we're decreasing all the way until it's flat, and then we keep decreasing all the way until 1. We're also decreasing from 9 onwards this way. Where is it concave up? Well, we can't know that. Because if we've got a function that's decreasing, it could be decreasing in a straight line, it could be decreasing concave down, it could be decreasing concave up. So not enough information for concave up and concave down. We just can't know. Local minima. Well, there's a minimum when we've got a decreasing function, and then we've got an increasing function. And right here at the middle, you could have a flat slope, or you could have a corner or a cusp. So like, for example, here, this cusp is a local minimum. That corner is a local minimum. That flat tangent line is a local minimum. All three of those. So where are we going from decreasing to increasing? Happens right here at x equals 1. We were decreasing, now we're increasing. So that's a local minimum. Does it happen here where there's a flat slope? No, because we're decreasing, then we go flat, then we keep decreasing. So because we never went up, this isn't a minimum. Here's a flat one, but we're not going from decreasing to increasing. So x equals 1 is the only local minima. Local maxima, that's where you were increasing, and now you are decreasing. And that happens right here at 9 and nowhere else. So local maximum at 9. Okay, points of inflection. I would accept not enough information because we don't know anything about the concavities, so we can't know where the concavities are changing. You could deduce one point of inflection here, but I wasn't going to take off points if you didn't deduce it, because it was a very special circumstance, and in general, you can't know if there's a point of inflection if all you have is the f prime values. Global minimum and maximum. Here we definitely don't have enough information, because I only told you how steeply things were increasing or decreasing at particular points. But for all I know, for example, between 3 and 5, well, we could be increasing not that steeply here, but we could be increasing very, very steeply right in here, and then a little less steeply. It could be going sort of up, and then up a whole lot, and then up a little less. So what I'm getting at is if you only know if it's going up or down, you don't know in these middle sections how far it's going up or down. So there's no way to guess at what the actual f values are. So you can't know if this local maximum, you can't know if this local maximum at 9 is a global maximum, because over here when our function was decreasing, maybe the f function started out at a higher value over here and just decreased, and then this local maximum is a local maximum, but we never made it as far up as it was originally over there. So not enough information for global maxes or mins. So that was all pretty fast. You know, that took me about 4 minutes to explain out loud, but if I'd just been chugging through, I was hoping that was going to be about a 2-minute problem. Oh, and I almost forgot to tell you. So you could deduce that x is -3 has to be a point of inflection, and here's why. Because I know I got a flat slope there, and I know I was decreasing, and I know I was also decreasing. Okay, so the argument I'm going to make is in this section we have to be concave up, and in this section we have to be concave down. If there's only going to be one critical value here, and that critical value is going to be a flat tangent. The reason why is because if I'm going concave down here, that means my slopes are decreasing. So there's no way that my negative slopes are going to continually decrease and reach 0. At some point I have to have them start increasing so that way they can get to 0. You know, if there was a corner or a cusp there, we could be decreasing, and now we got no problem. So it's the fact that it's a 0 slope here that means that I think this section has to be concave up. A similar argument applies over here, where it has to be concave down. If it was concave up, you know, I would have I would have positive f prime. I would have increasing f here, which would mean I would have to turn it around, which would imply that there was another critical value which I didn't list. So that's how you know that can't be happening. So I think for those reasons you can deduce that there had to be one here, but again, I wasn't taking off points for not figuring that out. Alright, let's look at part B. Okay, so here I give you the second derivative values, which tell you if your f function is concave up or concave down. So here it's concave up, concave up. Here it's neither concave up nor concave down. Here it's concave down, neither, concave down. So the only point here was you could find where the inflection points are. So I know here I was concave up, here I'm concave down, so here must be a point of inflection. If I'm concave down and then flat and then, sorry, not horizontal, so if my slopes are not changing here, so my slopes are decreasing, here my slopes are not changing, here my slopes are decreasing again. This does not count as a point of inflection, because point of inflections only happen when you change concavity from negative to positive or from positive to negative. So the answer here is you got not enough information for kind of anything except that x equals 7 is a point of inflection, and that's all. Oops, my bad. We also know where it's concave up or concave down. So it's concave up here all the way through there. It is concave down here all the way through the end. And that's really the only stuff you can know. So you can't know if it's increasing or decreasing, because again, you can be concave up while you're decreasing, or you could be concave up while you're increasing. Either one works.